Before I introduce our experts for today, I want to learn just a little bit more about you. Tell me, what best describes you? Where are you in your career? Are you an undergraduate or a hobbyist? Sorry to everybody, I have to put those in the same category. Are you an engineer? Are you a senior engineer or higher? If you're a CEO, that counts as you. Or are you something else? You're not an engineer. I feel bad for you. It's sort of the best profession there is. So I'll give you a couple more seconds. And we'll have a look. You ready? Cast your votes. That's the best way that you'll go home with some free hardware today. Alrighty, cool. Those are our answers. 5% hobbyists, 30% engineers, 55% senior or higher, 10% not an engineer. Sorry, you're probably not going to enjoy this. This is the engineer's guide. But without any further ado, it is time to meet our experts for this session. So, using the React function down the bottom left of your screen, please put your hands together for Henrik, Patrick, and James. Here they are, and they should arrive any second now. Yeah, there they Now, would you give the audience just a quick hello and tell them why you're here today? Let's go left to right. So we'll go Henrik, Patrick, then James. Who are you? Why are you here today?
My name is Henrik Flodell. I do marketing for Alif Semiconductor. I am based in our headquarters in Pleasanton in the Bay Area, and I'm here today to talk a little bit about the importance of going through model training when you're trying to deploy a system, an embedded system that you've designed to perform a specific task. We work with a lot of customers that are doing all kinds of applications that include some level of artificial intelligence. And we very often, when we start having conversations with these companies, they ask us, hey, can you just give me a model that can do this thing that I want to do, and that can do it super accurately and never ever make a mistake? And I'd love to be able to do that, but it's very hard to get to that point. And especially since we kind of come at this from the hardware side, you know, we're silicon guys. So that's why I wanted to introduce all of you on the webinar to Patrick and James, because they're really the person that can help you with this task.
Kick it off, Patrick.
Hi, my name is Patrick. I also do marketing here at Roboflow. I really love drawing bounding boxes around objects while getting a dataset ready to train a custom model. Perhaps maybe I can solicit another React. Thumbs up, thumbs down. Do you like drawing bounding boxes around objects? I see a lot of claps. All right, that's it for me.
Yeah, I'll give you a thumbs up. Why not? Get some thumbs down too.
It is very tiresome drawing bounding boxes.
James?
Yeah, hello everyone, I'm James, I'm based in Scotland, and it says technical marketer on the slide there, but I think the best description of what I do is I help people train models. I've trained models detecting everything from Scrabble tiles to shipping containers to metal defects, whether it's something that's ready for production or something for fun, I'm there to help. And like Patrick, I don't mind drawing bounding boxes, but I also like it when big models help me do that too. So maybe we'll touch on that later today. I'm excited to hear all of your questions. And yes, we like hard questions, so don't hold back.
Brilliant. All right, now I'm going to give the companies each about 3 minutes just to tell you who they are, to give you some sort of foundation to who you're talking to today. So Henrik, would you please kick us off?
So at Alif Semiconductor, what we do is we provide microcontrollers that are AI enabled. When we say AI enabled, what we mean by that is that we have added features in our microcontrollers, hardware level features, that can accelerate the execution of neural networks on the device itself. That was something that was not common at all back in, I think it was 2019 when we started kind of developing our silicon architecture. Nobody was really putting this capability into microcontrollers. There were a lot of cloud-based systems that were, you know, specifically targeting doing these kind of things. So essentially you had what we now refer to as an endpoint device or an edge device, recording everything that happens around it, and then pushed all that data to the cloud, and then sat there patiently and waited for a result to come back of the processing of the data. And then it would, you know, inform the user that, yeah, 5 minutes ago, this thing happened.
Not good enough.
No, I mean, you know, it was good for the time, But as things progress, people want faster answers. They want to be able to, on some levels, protect the information that is being processed from being snooped on, and then not sending it to the cloud is a pretty strong guarantee that nobody is able to access that data in transit. And also because the use cases evolve. There is on this slide here an example of such a use case. There is a lot of research and development and design activity going into not VR devices these days, but AR devices, essentially eyewear that has some level of intelligence so that it can augment your reality with things like, subtitles for languages that you don't understand, or being able to automatically transcribe what somebody is saying to text. Imagine you're at an airport and there's a gate announcement. Maybe you get that as a static symbol up in the corner of your screen so that you don't forget where you're supposed to go once you're done going through security or wherever you're currently located. So there's all these use cases that are now kind of shifting from the cloud down to the device directly. And it's really pushing the envelope when it comes to what you as a designer have to pay attention to when you're creating these devices. Because the old standard components that were used to make embedded systems, they don't have the horsepower or the low power characteristics or capabilities to be able to really take all this intelligence that were deployed in the cloud and run it natively on the device always. And there's a lot of things that you have to kind of think about when you are doing the AI model development, because you want the model to be fast, but you also want it to be accurate. And in a cloud setting, fast is not a problem. Throw more servers at the problem. There's an infinite amount of resources up in the cloud, but on device, like Patrick was talking about bounding boxes, you have a very strong bounding box over the resources that device has. So you better figure
that. I like that. That's good.
To use to your advantage. I think there's another slide in here.
There sure is.
Fantastic. So what we did at Alif to kind of enable this movement of doing the intelligence on the cloud down to the device was that we integrated MPUs directly in our silicon. We decided to do that with a licensable MPU platform. We didn't want to design a proprietary bespoke system that would then only be supported by us on the tooling side, on the software side, because we're a hardware company. We're very proud of the performance of the hardware that we create. But at the end of the day, unless there is software available for you to take advantage of the fun things that we do on the register level, you're not going to be able to be productive with this hardware. So for us, developing, nurturing, and growing a software ecosystem that can help the users of our technology become productive day one, and to not go down, rabbit holes that doesn't really lead them to, be able to realize what they're trying to do, is very important. So, especially when it comes to things like vision-based processing, because that's something that microcontrollers traditionally have had a lot of problem to do, because they're not huge number crunching machines. They're very tiny devices that are designed primarily for low power consumption and to do, slow moving real-time tasks. So this vision processing is kind of a new thing. And we get a lot of questions from people that are working with our silicon on, well, how do I actually design the intelligence in my application to take advantage of all the goodness that you put in the hardware? And this is something that Roboflow is a perfect example of, a company that can, they have some really smart things around not just optimizing the AI models to work well on these kind of devices, but to design the data set that you use to train the models so that they become as accurate as they possibly can be, so that your system does not make needless mistakes. And I want to throw it over to Patrick and James to describe how they go about achieving that a little bit.
Man, I feel like we might not even need to do a Roboflow introduction after that nice explanation. Real quick, so Roboflow, one of our catchphrases is, give your software the sense of sight. Essentially, in reality, what that means is we have a software platform and open source tools that help people create computer vision or vision AI models, integrate them into their software, create automations that can make some existing devices smarter, and then most importantly, get it into production. And I think perhaps most importantly is, one of our aims is to allow people to do that without necessarily needing to be a PhD in machine learning yourself. I've seen many software developers where they're incredibly smart, really good at what they do, but creating your own computer vision model and then getting it into production is maybe not the easiest thing that you can do in this life. So we have a bunch of tools to help people along that journey. And perhaps the best way to actually demo this or just get to know RoboFlow is with a demo. I don't know if we can go into that right now, or Elliot, if you have another slide to look at.
Yeah. I just want to ask a quick question before we go into that. Just a bit about the experience of people who are here today. Have you trained your own vision model before? That could be classification, that could be detection, any flavor of vision model. Have you done it before? What's your experience? Go ahead, give us a vote in there. Brilliant. It's neck and neck at the moment. We've had 50% yes, 50% no. Oh, yes is actually winning now. Brilliant. And that should help us to get to know our audience. Here we go. So 53% say yes, 47% say no. That is brilliant and close, and I think this is the perfect audience to talk to us about. Patrick, James, give us a demo of what you're doing over there at RoboFlow.
Let's do it. So before I joined RoboFlow 3 years ago, I never trained a vision model before. A day later, I had a vision model that detected something on my desk. And I thought, that's incredible. Like, I know how to code, but I wasn't in this world of being able to detect the location of an object in an image, nevertheless be considering, how do I run that in real time? How do I build logic on top of that? How do I integrate it into my manufacturing system? How do I make this kind of vision software the brain of what I'm doing? And so I'm going to show off RoboFlow, and I'm going to talk both about our platform, but also pepper in some tips more generally about how you should think about building vision systems. And Elliot, can I get permission to share, please? And then I will get to the demo. Let's do it. Okay.
Brilliant.
We are here. Okay, so this is RoboFlow, and I'm going to introduce a problem that frustrates me sometimes. When I go to the supermarket, I buy some juice boxes and it's missing a straw. And my only alternative is to pierce the top of my fingernail and try and suck it in, and there's no decorum, there's nothing there, it just spills everywhere. And so wouldn't it be nice? Yeah. See, it's a common problem. Wouldn't it be nice if the manufacturing line could catch these defects? And so we know that manufacturing facilities have increasingly advanced technology, and vision AI is among that. And so what we're looking at on my screen right now, this is a classification model. A classification model takes in an input image and assigns a label to the whole image. And here I just got juice boxes on my desk. I took 89 photos with my phone of the boxes at different angles, different defects, and I trained this classification model. It's a ResNet 18. This can easily run incredibly fast at the edge, especially if you have GPU or other kind of hardware acceleration. And if I go through these, we've got a loose straw. If I go this one, acceptable juice box. Classification is kind of the heart of computer vision. With that said, increasingly, we see our customers using object detection models. I'm going to go over to this tab here, where that bounding box thing, instead of getting a label for the whole image, we get a label for a region of the image. And what this means is that we can detect 10 juice boxes at the same time, and that's taking roughly the same amount of computational power. It's processing the same image, it's just the outputs that are different. So if I cycle through some of these images in my test set, different location, different defects, this one's acceptable. And we can see that our model is doing its thing, and it's confident in doing so too. And so you might be thinking, okay, how do I set about building a system like this? If you're in a manufacturing facility, we often see our customers will shut down a line for a little while and manually kind of simulate some of these defects that they know to be a problem. That's the rarer case. The more common case is just consistently collecting footage and finding those defects, uploading that to a dataset management tool like Roboflow, and then training a model with a tool like ours. So I'm going to go through and just show you what a dataset looks like. So here we are. I'm going to go in here, and this is one image in my data set. I'm going to delete this and kind of draw that bounding box for us. I go to the bounding box tool, and then draw a box. And you can kind of think of this process of labeling data as almost like teaching someone an entirely new skill. Like if you're trying to teach people to understand different types of classical architecture, you show them different photos of different buildings and different environments, and then you help them build the common characteristics. The same too is true of vision. So here we've got a loose straw. I'm going to label this with a loose straw class. And then I keep going through my data set and drawing those bounding boxes. Here we've got one labeled as acceptable. Here we've got one where the straw orientation is incorrect. So here it's like we're relying on the model to, okay, so juice box, cool, but the straw's the wrong way. It's pointing up instead of down. And we can kind of go through and see these defects. And one advantage of doing this dataset management in the cloud is we can do some powerful things around semantic similarity search, especially for bigger datasets. But we can also filter. So let's look at a few examples with no straw. And we'll go in here and see, okay, this is what an image looks like with no straw. You can see if I zoom in, it's got the glue there, but the straw is missing. And if I got this as a customer, I'd have orange juice all over my keyboard. So kind of with that in mind, once you've drawn enough of these bounding boxes, you get to training a model. And training a model sounds confusing. It sounds expensive. It sounds time consuming. Honestly, though, we see like this data set maybe took no more than an hour to train. A couple hundred images maybe take a quarter of an afternoon to train. The architecture that I use for this is called RFDetter. RFDetter is open source. Patrick's going to talk so much more about this later. But generally, RFDetter, state of the art, is real time. It achieves the best performance on benchmarks for object detection, and it's fast too. And so this is kind of consistent of a theme of these models are getting smaller, they're getting faster, they're getting easier to run locally. And that's why we're so excited to be working with more and more edge hardware. It's like our customers are running these at the edge in facilities, or they have centralized compute on a local network in their facilities, and they need these insights right now. So going back to Roboflow, if I take a look at this model that I trained, this was the object detection one, and we got lots of different tools at our disposal. One of them, if I go to our model here and go back to where we were earlier, is some metrics for our model. And we kind of expand upon these with a model evaluation. And this evaluation takes all your data, it runs your test, your validation sets, and gives you lots of charts to help you understand how your model performs. Now, this one with the juice boxes, 61 images for classes, controlled environment, that's very easy for the model to work out. But if I go to something like a warehouse safety model, where if I look at this here, I'm identifying forklifts and people, and there's lots going on, then that graph starts to look a bit different. And so by doing all this kind of model training in the cloud, that we can see this information. And then if we did it in a notebook too, we could calculate some stats too. But that's my kind of one big tip is when you're training a model, consistently look at your training graphs and consistently look at your evaluation graphs. What are they telling you about your model? And in this case, we can see our optimal confidence threshold we'd run our model at is at about 51% based on the trade-off of precision and recall, something that maybe we'll dive into a bit later on. With that said, I'm also going to quickly touch on what deploying this would look like if you were to use Roboflow, use it in the cloud, use it on your own hardware, whatever. You just click deploy model. And then when you do that, you can choose between a variety of different pre-built and build your own workflows. We can chain this object detection model with classification. And if you believe it, that can run in real time with the right hardware. We have one customer that is detecting whether or not the correct lid has been put on the correct pot of a consumer packaged goods to help reduce the number of times that supermarkets come back to them saying that products have been mislabeled. And they're running that in real time at a line that's processing thousands of containers every minute. And similarly, we can cycle through these, some conditional classification, some branching, you can do video analytics, all the more to do.
That's awesome.
Yeah, thank you. And with that said, the kind of possibilities are endless. So I opened up a few models I've trained. This one's detecting boxes on a conveyor belt. This was 260 images, different lighting conditions. And this is actually an assembly line that we use for product demos, sitting in the world's smallest manufacturing center in New York, as we like to call it. We've got one for glass defects where I can't even zoom in far enough to show you how small these are. It's getting the location of chips right on the rim of this and slight cracks on the rim at the bottom again. So again, the versatility, if you can see it, you can train a model to identify it. Another one I've got here is metal, detecting that scratch on a on kind of a focused image. This was 260 images. And then finally, I'll go back to this warehouse safety one. And this is detecting forklifts and people. And that's about 400 images from that bird's eye view. This was high-res imagery that we processed in the cloud. And then we have the capability to deploy on our own hardware. And then that kind of chasm of, okay, so I've got this model, then what? That's really when like we go into our workflows tool and be like, what do we want? What do we want? We can put our detection model, our bounding box visualization, our label. We could even add in object tracking, as simple as pressing the add button and just say, track, please. In fact, we'd do that just after here. We'd say, add in object tracking. And now we can do stateful object tracking across video frames. And the possibilities there really are endless. With that said, just to kind of show you this working, I have a demo that I prepared earlier. And if I run this Python script, which is using Roboflow, this can run an inference server on your own hardware, centralized system, on edge devices, whatever your deployment looks like for you. It can be, honestly, a lot of our customers use local deployments because they need that privacy, that security. And then we get the result of this image that showed that incorrect straw orientation. It got it solved. So yeah, if models are getting smaller, models are getting faster, they're getting more accurate. Roboflow is at least trying to be at the forefront of that with some of our state-of-the-art research. And to call back to what Henrik said earlier, changes are happening at both the hardware and the software level too. And so we're kind of excited to see more people using vision AI in real-world applications to solve problems, literally from the microscopic all the way to manufacturing, all the way from indexing and inventorying to consumer applications. So yeah, that's all I've got is by ways of demos. One final thing I'll plug is if you're like, okay, can I train an open source model with my data set? Absolutely possible. If we go back to our version that we trained, we can hit download dataset, take that dataset. And if you'd like, we have notebooks that cover basically all of the state-of-the-art object detection models, as well as segmentation on our GitHub, Roboflow/notebooks. You'll see RFDetter, Google Gemini, YOLO-E, Qwen, Polygemma. So whether you just like playing for fun with state-of-the-art models, or you want to evaluate different solutions, or you prefer the control of a Colab notebook, that solution exists too. And so with that said, that's all I've got. Let's get in some questions, I think.
Now, before we go to a question, because I actually got some here. Was that a cool demo or what? Is that a hell yeah, that was a cool demo, or a no? I don't know why you vote no, because that was fantastic. Now, by the way, I've already got one question here, and usually we're going to leave these to the end, right? But I just want to touch on it right now. Are these workflows deployable on the edge? Yes or no?
Great question. So yeah, the typical configuration, when you see a workflow and you're like, oh, this is on the web and it's in that interface, like what's going on there? For the engineers here, we have written our own domain-specific language that we call workflows that is turning all of that into, in fact, am I still sharing? Does that still work?
No, sorry, it's got a hole on the screen now. You can't see it.
Okay, no worries. In that case, then, if you're in workflows, there's a little developer icon in the bottom left. We kind of hide it because most people don't need it. You'll see JSON, and that JSON is what's running on the device. We see a lot of people use kind of GPU accelerated devices on the edge, and realistically, they're realizing dozens of frames per second on real-time production workflows running on their hardware. We are adding some device management capabilities in the future, but yes, runs on the edge, runs in the cloud, runs on your own GPU, runs on AWS, wherever you want it to be. Because as Henrik says, like if you're deploying these systems in your manufacturing environment, you shouldn't need to be sending images to the clouds 24/7 to get those insights. You should be running on the edge with robust hardware.
Brilliant. There you go. 85%, 86% said cool demo. You got 6 haters in the audience today. we'll get
That's
down
okay.
to the bottom where they are.
There's always next time.
Now, I would love to transition now to a panel. I want to ask you some questions that are designed to get the insights out that people who might just be starting with vision AI, vision machine learning might want answered. Now, we're just going to start basic, very basic. What is the big difference between models that run on the edge versus ones that run on cloud service? Patrick, I'll chuck this one to you first.
Oh man, I would say off the top of my head, I think this all boils down to something that Henrik was talking about earlier in terms of speed, latency. Cloud vision models are really great for handling general challenges that you see out in the world, but with that comes along a little problem in terms of the size of the model. If you want to run a really gigantic general purpose pre-trained model, you might need access to some expensive, limitless amount of computing power. But that would be fun. But not everybody has that. You know, when you're talking about a situation where let's say you want to take inventory of shipping containers in an intermodal yard. Your compute may be mounted on a vehicle that is driving around that parking lot, and you won't have internet connection. I think in this situation, edge models are smaller, they can run at lower latency, and typically they're designed to tackle a challenge that is domain specific that those general purpose pre-trained models won't be able to help you with.
I can just add to that as well. I think that this, just exactly the scenario that you described, this is one of the challenges that might not be obvious at first when people are kind of approaching, well, I want to create a system that is based on artificial intelligence to solve a problem. And I don't know why this is still a thing, but I keep seeing people kind of coming at it from that perspective of, well, if I just have a large enough model that knows enough about absolutely everything, then of course I can solve the problem. And it's like, that's kind of the wrong way to go about it. You probably want to start paring down the problem so that you're focusing on exactly the scenario that you want to handle, that you want to solve, because otherwise you'll never really get out of that latency trap, because now you have the biggest model ever that can answer exactly every question possible, but you have to drive that golf cart around the stocking yard very, very slowly for it to have any chance to, processing all the containers that it sees. So to kind of figure out, how do I draw a box around specifically what I want to try to solve? And then how do I find or develop? I mean, it's not always necessary to develop a solution from scratch. Sometimes you can take an existing solution, but just train it on specifically the task at hand. What do you want to achieve? That is something that I think, people they're starting to kind of come out of the mode where, well, if I just have enough AI, I can solve everything. But how do I actually get the AI to be right-sized for what I want to achieve? And instead of focusing on a big model, try to focus on a high accuracy level.
Henrik, I like where you're going with that, because you actually perfectly segued me. How can engineers make use of pre-trained models? Sometimes it feels like there's so much variability. Everybody's system is different. Not everyone is using this specific camera. how can I make use of pre-trained models despite system variation? And that one goes out to you, Henrik.
Yeah. So, I mean, that board that you just held up, our AIML app kit, one of the things that we do for that board is that we publish on our GitHub a whole bunch of pre-trained models that you can run on it. So we have an SDK that allows you to collect live data, camera data, audio data, vibration data, that type of thing. And then we have pre-trained models that can process that data. But that's not really why we made the board. We wanted to make the board a vehicle so that you can try your model on live data as quickly as possible. So, we don't mind if you run our pre-trained model, but those models aren't really going to be turnkey for any particular use case. But it gives you an indication of performance. It gives you a very quick kind of starting point where you can see that, all right, now it's doing, roughly what I would need this thing to do. Now I can take Alif's pre-trained model out and I can start working on the specific model that solves my problem using a data set that is adapted for how I'm going to deploy this system. With vision-based systems, I mean, you have to think about a lot of parameters, because if your camera is mounted high up versus kind of face level, that has a huge impact on the resulting quality of the data set. If you kind of look at James's bird's eye view of that warehouse with the people and the forklift, if you have trained that model from a camera that is mounted at eye level, you're not going to have any accuracy whatsoever. It needs to be, representative of how is this system going to actually be deployed and put together.
Patrick, you got your hands up. What's up, mate?
Nice. Yeah, I wanted to add to that too, just on top of what Henrik was talking about in terms of pre-trained models. I think one trend that we see at Roboflow is using a big model to help train a small model. During James's demo, you may have seen like manually drawing labels around an object. But if we kind of look at the whole process of developing your model in an environment where you do have access to the internet, larger models, and then preparing this model to go out into the world where it will be operating in limited resources, we're kind of moving towards a place where we don't have to manually label things by hand ourselves all the time. We can use those pre-trained larger models to help identify and help us generate those labels, and then we just need to review them. And then this can drastically speed up the time that you spend labeling your data set and preparing it to train that smaller edge model. We could maybe talk about this a little bit later on as well, but that's kind of my 2 cents there.
I'm keen. I've got a question for our audience today. Remember, vote. That is honestly your best way to go home with some free hardware. Have you used a pre-trained model before to speed up development? I've done it recently, mobile net. It's fantastic. It really did speed up development. So you got, yes, you have used a pre-trained model. No, you haven't used one before, or you didn't know it was possible. So get your votes in now. Brilliant. And now, might I add, I love speaking to each and every individual in this audience today. We've got such a great turnout today. I think there's 65 people who have come, spend some time of their day here with us. And for that, we massively appreciate it. We're hoping you get something out of this session. Let me show these results. So 67% who voted had used a pre-trained model before. Fantastic. We've got a good audience here. 31% no, and 3% didn't even know it was possible. That is awesome. Now, I would like to give it back here, right? What's the best piece of advice that you can give to engineers on how to train a solid vision model? Patrick, let me pass that one to you first. What's the best advice you can give people about training a good model?
Yeah, my first piece of advice is always to find the right training data set. For example, if I want to be checking juice boxes as they move down an assembly line, the best case scenario is I use the data from my assembly line, and it's coming from the same camera that will be used to actually monitor those juice boxes in production. There's a lot of things that can change, sensor quality, lens, focal differences, stuff like that. So you want to try to use the correct data set when you're training your model. I have a quick story about this, which is Audi, the car maker. They have an application where it has a couple computer vision models that were trained in RoboFlow. And in this Audi smartphone app, if you see like an indicator light, everybody's been in this situation. There's like an indicator light in your car, it turns on one day, and you're like, what the hell does that indicator light mean? Well, now it's like in the Audi app, you open up your phone and you point it at the indicator light, and it can use computer vision models to understand it's an indicator light and then understand which one it is, and then it will show you the user manual entry for that. And I was talking to the person who developed this.
Dads have lost their jobs. They're the only ones who can read the car manuals.
Hey, it's actually a great example because it's like I've never opened the car manual, so it's like just allowing.
Come on, you're an engineer. Figure out how the engine works.
As an ex-technical writer, I really like getting the documents in front of people more easily. Used to cry writing documents that nobody was reading. But my lesson here was I talked to the developer and he said, at the beginning they were collecting data, right? Taking pictures of the inside of these Audi vehicles, and they started with these really nice DSLRs where the images are like crisp and beautiful, contrast is great sharpness. And they started training, but then later they realized, it's not that great. Actually, what we need to do is we need to start collecting the data with our mobile phones. And so he had like 50 different people use different mobile phones to take pictures of the inside. And if you look at it, the photos, they're not beautiful, they're not good. There's like horrible glare and just like bad contrast and stuff like that. But in the end, they used the worst data set to make the model, and the model is more accurate because it is representative of the actual real world production environment.
Now, I've got a question for the crowd, because we're all here to learn and some of us are more experienced than others. Has anyone else got any helpful advice for new beginners on training a solid model? I think the best one that I've heard is just the classic, like, garbage in, garbage out. I've had experiences where I've trained models and I've given it some garbage in and it's given me garbage out. So has anyone got some helpful advice or sayings for new beginners on training solid models? Now, if you do, use that question function and I'll know that's actually a statement. Go ahead and add something in and we'll read them out shortly.
Am I allowed to raise my hand?
Oh, do you want to raise your hand? Go on.
Yeah,
Go on,
yeah. Let me raise my hand because I've got a list for you, and I'll try and do rapid fire. So knowing that there are some more seasoned developers in here, maybe this information's especially appreciated. Number one, Patrick said representative training data. Ideally collect from the camera that is going to be used as input data. Also, if you're detecting multiple different objects, make sure your classes are balanced, which is to say, if you're trying to identify 6 different defects in metal, a scratch, a dent, a blemish, a mark, a piece of plastic on the side, whatever, make sure that you collect enough examples of that. If you're training a model with 150 images, there should be 20 at least of each of those classes. If it's 1,500, if you could get 100, 200 of each, please do that. That's like the number one mistake that I see people make. It's like, oh, I've got 2.
Real quick about that.
Go for it.
I've got 3 different classes. Am I splitting those images completely equally? Like I can't have 500 in A, 200 in B, 50 in C. Like you want them to be equal, no?
We want it to be as close to equal as it can be. It doesn't need to be perfect, but certainly the more examples you have of each, the better. And if you collect 10,000 images with no defects and 5 with defects, your model isn't going to be very good. That's like quizzing like a kid on architecture with only showing them 5 buildings in the world. Like, how would they know?
Yeah, copy. You got any more rapid fires for us?
Yeah, and let me try and do even rapid Semiconductor, whatever. So continual learning, like your model, think of it as like a living thing in your facility, like continuously collect data from your assembly lines or wherever your model's running, bring that back in to train future models. So if your model's running at 80% accuracy, keep getting data, use that to get it to 90, 95, 100s. Also, one thing, large models will never know your production data. They've never seen it. You have your production data. That's my like quick one-liner on why use a fine-tuned versus pre-trained model. If you're doing object detection, bounding boxes need to be as tight around the object as possible. Try and include as little background information such that the model actually sees the thing you want to find, and that will make those bounding boxes tighter in production. And then finally, keep your eye on state-of-the-art research. Plug for Roboflow, we set state-of-the-art for object detection and segmentation this year, but things are changing so much. And that is to say that your model might be state-of-the-art now, but in a year, it's probably going to be a different architecture, a different version. So indeed, it is the case that a model may be running now very well, but think of how much more accurate it could be in the future as technology develops. So a couple things, hope it's helpful.
I want to quick fire one more thing. So we've talked about advice on this. What are some common mistakes? Quick as we can get them out. James, you want to kick this one off as well? What are some common trip-ups?
Okay, yeah. Okay, number one, don't add every augmentation. Augmentations help you increase the number of images in your dataset by adding effects like grayscale, which is helpful for color agnostic deployment scenarios, by increasing contrast where that's relevant, by tiling images up, which is good for like aerial imagery from drones. Don't add every augmentation. Start training your first version with no augmentations and layer in ones that are relevant. I see like so often people are like, oh, more images, great. More images isn't good. Like you say, garbage in, garbage out. Secondly, you don't need 1 million images to train a model. Try with 100 first, see how well it does, and go from there. Other mistakes that I see people make, I guess, not putting enough time into the planning phase. If you're going to be developing a model that needs to run in real time on the edge for detecting juice boxes, because please don't give me another juice box with a missing straw. You're going to need an object detection model that's going to need to run in real time. You're also going to need object tracking so that you each frame has information about the previous frame and you know unique juice boxes rather than using classification where you don't have that. If you go train a classification model, you're going to have to go back to your team and say, we need to relabel this for object detection. Don't do that. And then also, finally, don't be like me and draw your bounding boxes. We have a tool that can automatically label in Roboflow, and increasingly in the theme of using big models, you can use, we've got a tool that's called AI Label Assist, which uses a huge model that runs in your browser, and huge as in like bigger than these ones we're talking about, and will let you just point at something, you click on it, it will let you label, which is to say, don't be like me and draw 100 bounding boxes, just point at the thing you want. Like, this is how technology is growing.
Patrick,
we're kind of moving down the path of using AI to teach AI how to solve AI problems.
Yeah, what are we getting ourselves into? By God. I thought you said you liked the bounding boxes.
I lied. We
All
lied.
in moderation.
Well, yeah, everything's good in a little bit. Patrick, I want to ask you a question which I told you I was going to ask it, but it's still sort of a tough question as such. Tools like yours, right? Machine learning operations platforms, but specifically yours, does it make simplifying assumptions that could result in a less optimized model than you could get in manual training? In other words, like, does your automated pipeline with your beautiful website, it is gorgeous, right? But does that lead to inefficiencies that come from automating it itself and not like manually training it like a real hard ass in MATLAB or something? You get what I'm getting at?
Yeah, and it's an interesting question. I think that we should break it up into a couple pieces and think about sort of like the topic or maybe the goal when you're training, right? I think when we are talking about making vision models that should run on edge devices, performance is in the eye of the beholder, or performance is in the processing power of the GPU that is running. So I think that the nice thing about RoboFlow is we have our own platform, but also alongside that, we have a lot of open source tools that we can create. And I think that basically what we're going for is to, I guess, open up possibilities and give people more flexibility when it comes to fine tuning, or I should say fine tuning, not in terms of the actual phrase that is used in computer vision, but like getting the exact model that they need so that it will run at the right accuracy and latency for their specific environment. I did have like a couple slides that I could share related to this if I could get some permission to share that.
Yeah. I want to have some time for the Q&A.
Totally, yeah. Let me see here. Ask the organizer to make you the presenter. That's what I see right now.
Now a presenter.
Yeah.
Right there, man. Go ahead, present away, but be quick.
Got it. All right. Well, yeah, so, you know, related to us making tools and open source models that can help people get like the best performance at the edge. You know, earlier, James was showing off a couple different kinds of computer vision models related to classification, segmentation, object detection. We didn't really see key point detection earlier, but that's something that people need. Now, if you're like me, I wanted to keep it juice focused today. So I was working on a model that uses segmentation to find the fill levels of juice in these bottles as they are filling up. And, you know, you might be familiar with these kinds of Pareto charts that show off the accuracy and latency of different off-the-shelf vision models. Here I have a couple examples. There's a YOLO V8, YOLO V11. These are very often used out in the industry. Well, James mentioned this earlier, but RoboFlow recently released an open source model architecture called RFDetter. There's a specific segmentation version of this. And when we compare it to other models using the same benchmarks, you can see that we are outperforming the industry standard in terms of latency and accuracy. So if you look at that kind of lowest latency data point here, we're outperforming the previous architectures that were very popular by 9.4. It's an absolute, like, I didn't believe it. When the team showed this to me, I was like, what the heck? And they're like, also, it's just beta. It's just the preview. This isn't the official launch yet. And I was like, what are we doing here? So +9 MAP. So that's an example of how we're making things that are in our platform, but also open source that are just kind of bringing the whole industry forward in terms of accuracy and latency. All right, there we go. How do I stop sharing?
Mate, you're stuck there now. No, I'm joking. I'll fix that for you. Don't worry about it.
Let's go. Let's go, go, go.
Now, I want to ask about the joint solution, right? Because you're both here today. So an engineer who's come today, by the way, everybody, thank you so much for sticking around. We'll be revealing who's going to be winning the Alif AI ML app kit shortly. But how can someone take an Alif dev kit, you know, maybe one that looks like this, and take RoboFlow's tools and create a production-ready system? Henrik, would you kick us off? How do you two work together?
Yeah. So at least in my mind, the thing that the engineer needs to do first is to find a distributor that can actually provide them with the hardware, unless they win the war today in this session here. But Alif development boards are available from where you get your electronics for the most part. Folks like Mouser, folks like Aero, they carry our products. You can get one of our evaluation boards, and then you head over to our GitHub, github.com/alifsemi from memory. There you'll find our AI ML evaluation kit. And as I mentioned, it's essentially a couple of different pieces of software. There is driver layers, there is what we call board support layers that can collect data from live sensors that we have on the boards, microphones and cameras and things like that. And then we have our models, so with pre-trained models that you can run on that data. So play around with that a little bit and find a model architecture that seems to be able to support what you try to achieve. Then take that model and throw that model out. Maybe not the entire model, maybe just that particular version of it. You can go and get the model untrained from a source like Hugging Face, for instance, or wherever people find their AI models that they want to train up, then you head over to Roboflow, you set up an evaluation account, and Patrick, you take them through the rest.
All right, yeah. I mean, I'll keep it really quick, but I would basically say we should run through the process that we saw a little earlier with James, where if you head over to roboflow.com, you'll be able to play around with some of our tools that we have for managing your data set, training a model in the cloud, and then getting what you need to test it on some local hardware and then run it on platforms.
And I will add to that and say, if you are a student, we have a student plan, just responding to that previous poll, that's going to give you a few more credits so that you can build something. We see students from around the world using our tools for everything from research papers to fun. And then if you are a hobbyist and you're like, hey, I want to be able to detect juice boxes too, or go around the supermarket and find all the problems, or whatever you want to do. Yeah, I love juice. Whatever you want to do, our free tier will give you what you need to train a few models in the cloud. You can run those on your own hardware. You can manage data sets and so on. And then if you're doing a business application, of course, you can sign up for one of our paid tiers and start rolling on the business tools. So yeah, hobbyists, business people, engineers, facilities managers, all are welcome and love our software.
Brilliant. Now, we are approaching the end of this session. I just have a quick question for anyone who wants to go into the winning. Who would like to win some free Alif hardware? Give us a me or a nah. I don't know why you do nah, to be honest. You just go in the winning to win some free hardware if that's the case. Emmy has been watching the chat closely, so thank you to everyone who's been asking questions. Shortly, we're going to be going through the Q&A. We'll get through as many of it as we can. But we understand if you've got to drop out, we're coming up to the hour that we promised you. If you want to stick around, probably do about 15, maybe 10 more minutes worth of questions after this. Otherwise, fill in that survey when you leave. Now, 100% of people say they would like to win some free Alif hardware. Henrik, this one is from you. So thank you very much for donating the hardware. Shall we reveal the winner? I think we shall.
Yeah.
Miriam, thank you very much for coming along today. You will be taking home an E7 kit. Well done. Thank you very much. We've seen the questions you've been asking. Thanks for being a part of it today. Now, let me run some slides for you. It's Q&A time. Now, we have gotten so many questions. There must be 100+ questions in here, and I'm going to be handing that over to Patrick, James, and Henrik after if I don't ask it today. But I've got some ones that I want to throw out here. And gentlemen, keep the answers as short as possible if you can, so we can run through as many in the next 10 minutes. Now, Henrik, I think this one's for you. Do you see a growing market demand on large language models on edge devices, or is the cloud still the gold standard? Also, maybe you want to comment on the development of the edge towards large language models in the last couple of years. Now, I know you're doing something really cool over at Alif. What are you up to at the moment with large language models on the edge?
Yeah, so large language models, one of the foundational pieces of technology in AI land that enables them is this concept of a transformer operator, or a network known as a transformer network. So it's a special kind of essentially it's essentially the code inside the model that makes it do something. This is reasonably new technology. I mean, AI moves so quickly, so things aren't new for very long. But on embedded devices, this has been, something that you can do, but it hasn't really been a way to hardware accelerate these transformer operators until very recently. So at Alif, we introduced 3 new series of devices from our Ensemble line, the E4, the E6, and the E8. And in those devices, we use an NPU called Ethos U85. It's the latest generation of the Ethos technology that we integrated, and it can hardware accelerate those operators. So you can now actually deploy, there you go.
I've got one. Oh, my bad.
Eyes aren't deceiving me. So we can hardware accelerate generative AI type models on a microcontroller device for the first time. Now, people talk about LLMs, I like to call them SLMs when they're being deployed in silicon like this, because obviously we don't have access to the never-ending resources that exist on the cloud side. But again, going back to what I said, if you kind of think about the problem that you're trying to solve, just imagine that you want a model to generate some kind of text for a toy or something like that. Maybe focus that model on specific things that are related to who will be using the toy rather than answering every arbitrary question as possible. And it's very possible to run those type of workloads on embedded devices powered by small batteries today.
I love what you're doing over there with your language models. Now, I reckon we'll chuck this one over to Roboflow. What advice do you have for training a model to identify things that aren't commonly captured or don't have existing data out there? I think I could go one right now. Go get the data yourself. Go out there, take some photos. But let me send it over to the Roboflow boys. What advice do you have for training a model to identify things that aren't commonly captured?
I would say go to roboflow.com and start
brilliant.
playing around with ours.
Brilliant.
Well, there,
Roboflow, man.
I mean, that question is exactly the question that we see every day. There's this feeling that you get from everyday interactions with technology where, I take a picture of a dog and it's like, it knows there's a dog. And there are a lot of models out there that they understand everyday objects, and it creates this kind of illusion that we've already solved every vision problem, but there are tons of things out there that have not been solved yet. James mentioned those large models, they haven't seen the inside of your factory previously. So yeah, I've seen people start building a model on a factory floor where just to get a prototype going, they hold their cell phone over the conveyor belt line for 10 minutes and get their initial data set that way. So I think my recommendation is start small. Don't try to go for perfection right away. Collect some data, label it up, train a model, get going. Actually, your initial model, it could probably be used to help speed up development of your second, better model.
Brilliant. Here's another good one. What models from Roboflow are ready to deploy on Alif hardware? What's the link like here? You guys ready to work with each other? What models are ready to go from Roboflow?
I don't know if I can say we have any pre-trained models that we've made ourselves that are ready to go right now on Alif hardware. Henrik, do you want to add to that?
Yeah, so the enablement around our devices for deploying any kind of machine learning model is mostly focused on the framework that was used to create it. So we have a very straightforward path for deploying models that can be expressed as TensorFlow format, for instance. We very recently, last week, in fact, at the PyTorch conference in San Francisco, we announced that we have support now for Executorch, meaning that we can deploy PyTorch models directly to our devices. So within Roboflow, you can work with models that are developed in these frameworks, for instance, and then the process of taking the output of the Roboflow tools and converting that to something that can run on our parts is very straightforward.
Yeah, and I'll add to that and give some color on RF Dasher. So Patrick's chart there, like 9.2% map increase on segmentation, and we realized we hit, for anyone interested, over 60 average precision on the Microsoft Cocoa benchmark for object detection. In our first release, again, state of the art, we use PyTorch and transformers, and so most certainly, like what we are seeing consistently is transformers are the ways that we're realizing these gains. Traditionally, these models were convolutional neural networks, and we're increasingly seeing kind of a plateau in performance. Like you saw, like two previously state-of-the-art models were kind of the same on the graph, and those are like years apart in development. RF Detra, though, our machine learning engineer team got to work. We're at different parts of the chart. So yeah, keep following transformers. It's a revolution.
This is one funny question that I saw it right at the beginning, and I just couldn't help but laugh at it because you can't really say much to it. But it is, what are your customers up to? And that one was towards Roboflow. So if you want to speak to what your customers are up to, I don't know, there's probably NDAs involved there. But in general, we can probably answer that. What are your customers actually doing?
Yeah, I could talk about that a little bit. I think that computer vision, just like by nature, it's really good at solving industry problems where, maybe it's not feasible to have a human checking something all the time, or humans are prone to just error when they're looking at something, or perhaps it's something happening at like a speed that doesn't make sense for a human to handle that task. So we've seen a lot of customers where, it's in manufacturing and they want to keep defects from escaping the factory and then ending up in the hands of their users, because then their users are going to have a bad experience, or there might even be safety implications involved in that. James mentioned this earlier, really huge food processing company making items, making sure that the labels match the content of what's inside before it goes out to a supermarket, because there's also like allergy concerns and things that can go wrong if people are getting the food that they were not expected. So with computer vision you can create these models that help check every single food item or every single item before it goes out into the world, and you can avoid any kind of accidents and then improve quality. And then there's logistics. We mentioned it earlier, taking inventory automatically. I think my favorite thing that I saw recently was a research project where there's teams across a bunch of different museums that created an application to help them digitize these insect specimens that they've collected over time. This one museum, they have 8 million insect specimens, and they actually don't even know, it might be 7 million. And they're using computer vision to analyze these insects at scale so that they can like unlock some new research capabilities that you wouldn't have been able to do otherwise without a broad data set like that.
A worthy cause. Beautiful. I reckon that is where we end it. Now, thank you, everybody who's come to this engineer's guide. Any questions that we couldn't get around to in the question and answer, we're going to send you an email and get that answered. Once again, congratulations to Miriam, who's going home with the AIML app kit. Thank you very much to Henrik Funnel Alif, putting that one on the line. This one's mine, you can't have it. Make sure you make good use of it, because it's not every day that you get free hardware. One more thing before you go, there's going to be a survey when you leave. It helps us do better for next time. If you like something, tell me. If you didn't like something, please tell me. We take such great pride in our engineers' guides, and your feedback is very, very important to me. Other than that, thank you very much for our panelists. Give them a round of applause, and I hope you go on to have a great day. See you at the next one. Thanks for joining us, everyone.